Today, we're going to be solving a difficult number theory problem that has to do with sums of powers. It says to prove that there are infinitely many n in the natural numbers such that n divides 1 to the n plus 2 to the n plus dot 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 up to k to the n for some natural number k. Before we get started, make sure you leave a like, subscribe to my channel, and let's get on with the proof. In number theory problems like these, where we have lots of sums or differences of powers, we often resort to the lifting the exponent lemma, or LTE. Let Vp of n equal k be the p-adic valuation of n. That is, p to the k divides n, but p to the k plus 1 does not divide n. Or in other words, k is the highest power of p that divides n. Then LTE says that for a, b, odd n, odd prime p, then if p divides a plus b, the p-adic valuation of a to the n plus b to the n is equal to the p-adic valuation of a plus b plus the p-adic valuation of n. Basically, LTE says that if we have two numbers with the same power, the valuation of the sum of those two numbers is equal to the valuation of the sum of the bases plus the valuation of the power. We notice that the lemma deals with prime numbers. Since we know that there are infinitely many prime numbers, this is even more promising to us, and we take advantage by letting n be an odd prime. Keeping LTE in mind, we can begin our proof. Proof. Let n be an odd prime, and for some integer, k, we have that n divides k plus 1 and k is even. This will be very important later on, as we will see. Now we can consider our sum 1 to the n plus 2 to the n plus dot 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 up to k to the n, and we want to show that n divides this. We then rewrite the sum by grouping up the first and last term, so we have 1 to the n plus k to the n, grouping up the second term and the second last term, so we have plus 2 to the n plus k minus 1 to the n, and then we keep going until we meet in the middle at k over 2 to the n plus k over 2 plus 1 to the n. We note that there are k over 2 terms because k is even. Notice that in each of these parentheses, the sum of the bases of the exponentials is k plus 1. Clearly, in the first parentheses, the sum is k plus 1. In the second parentheses, the sum of the bases is 2 plus k minus 1, which is equal to k plus 1, and then so on. And then looking at this term, we see that the sum of the bases is k over 2 plus k over 2 plus 1. Combining these two fractions, we get that it's equal to k plus 1. Okay, let's use LTE on this first term. We have that the n-adic valuation of 1 to the n plus k to the n is equal to the n-adic valuation of 1 plus k plus the n-adic valuation of n itself. We apply LTE on each of the parentheses in the sum. So we keep going until we get to this term, right? And so using LTE on that term, on the last term, we have that the n-adic valuation of k over 2 to the n plus k over 2 plus 1 to the n is equal to the n-adic valuation of k plus 1 plus the n-adic valuation of n itself again. Remember that we defined k such that k plus 1 is divisible by n. That means the n-adic valuation of 1 plus k is greater than or equal to 1. Similarly, the n-adic valuation of n is simply 1. Then we note that the n-adic valuation of 1 to the n plus k to the n is greater than or equal to 2. Analogously, we show that the n-adic valuation of k over 2 to the n plus k over 2 plus 1 to the n is also greater than or equal to 2. So what does this all mean? It means that for each of these parentheses, we can rewrite it as some constant c1 times n to the 2. We can do this because we've just shown by LTE that each of these parentheses have an n adic valuation that is greater than or equal to 2. Or in other words, the highest power of n that divides the parentheses is greater than or equal to 2. So we can rewrite our sum as c1 times n squared for some constant c1 plus c2 n squared for some constant c2 plus dot 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 until we get to c sub k over 2 times n squared for some c sub I in the integers, positive integers. Clearly, this sum is divisible by n squared, and so we're pretty much done with the problem. We know that there are infinitely many primes n, and to choose k such that n divides k plus 1 and k is even, we can simply let k equal n minus 1. Then k plus 1 is equal to n, and we see that if k plus 1 is equal to n, then this is clearly true. A number always divides itself. Note that because n is odd, n is an odd prime, k must be even because k is 1 more than n. And so we are done. We proved something stronger. We showed that n squared, there are infinitely many values of n, such that n squared divides 1 to the n plus 2 to the n plus dot 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 up to k to the n for some natural number k. And so we are done. Thank you for watching the video. If you have any suggestions or critiques of my solution, please feel free to leave it in the comments. If you enjoyed this video, please make sure you like and subscribe, and I'll see you next time. Peace out.